thanks very much to Jonathan and Arup for having us here today. We're going to be talking today about some of the work we've been doing in Fdtd, finite volume methods up at Edinburgh. And in the first part of the talk, Brian, Hamilton, and I will talk about some of the computational and theoretical issues underlying using Fdtd and finite volume methods. And then, at the end, Craig Webb, one of our recent PhD graduates, will talk about this work accelerating codes for very large-scale problems at audio rates. Okay, so just before we start, I just wanted to say a little bit about computational cost, because acoustics simulation is a big job, no matter how you do it. And it's very useful to take a look at some of the operations that you have to make use of when you're doing a simulation in order to try to evaluate relative computational merits. So there are a lot of things to consider. So one that Jonathan talked about a bit at the beginning is just the raw degree of freedom count. That's important. But on top of that, there are all sorts of things that go under the hood when you're setting up the problem. So there are setup costs. And for example, meshing. So there's volumetric meshing that we have to deal with in 3D, also surface meshing. And also for methods like BEM, we have to think about how we determine all the elements in the coupling matrices. So that's an operation in itself. And then, when it comes time to performing matrix operations, which is going to be pretty much the main operation underlying all of these methods, are the matrices sparse? Are they dense? If they're dense, are they structured somehow so that we're able to exploit that structure using fast transforms like FOTs, for example? Is there a need for linear system solvers? If so, what kind? Can we use very simple linear system solvers like Jacobi methods, Gauss-Seidel methods? Or do we need to make use of more complex ones where we have to have a preconditioner? And if so, do we have to store the preconditioner, which could be big? And then, of course, the big thing these days, how do we get these to run in parallel? We just sort of rethink everything having to do with how these algorithms are built. And then, of course, there's the goal. So are we trying to get out a single room impulse response? Or are we trying to extract some key features of the room? So are we trying to figure out the T60s or when the early reflections occur? Or are we trying to do a full virtualization? So do we want to be able to have moving, like sort of an online moving receivers of sources? Do we want to have variable geometries, so doors and windows opening, that sort of thing? So all of these things kind of impact on how you would measure cost for a given algorithm. And then there's accuracy. So there are measures that are sort of thrown around, things like 10 points per wavelength, but actually, I mean, the main way to measure accuracy is going to have to be through psychoacoustic measures for these kind of problems. And I don't think there are at the moment good measures of such accuracy, at least in the numerical world. So I think just the point I wanted to make is I think it's really difficult to say that any particular method is best in general. It's kind of like saying there's a best car or something. You need to say best car for what reason? So any judgment, I think, needs to be problem specific. And this is the problem that we work on up in Edinburgh. And it's well encapsulated by something called the NEST project, which is a 5-year ERC-funded project. There are 11 of us, joint from the Acoustics group and the Edinburgh Parallel Computing Center. And the goal for us is to do large-scale audio rate sound synthesis and virtualization on parallel hardware. So we look at a lot of different systems. So typically musical instruments, so brass instruments, stringed instruments, drums. But a big part of the project has to do with embedding these in 3D environments, and that's where our interest in room acoustics comes in. So the constraints for us are that we want to work at audio rates, so 44 kilohertz and above, for large spaces. Our systems are highly nonlinear, and we want to have some kind of flexibility in virtualization for all these systems. We want to be able to move around them or move the objects themselves. So we decided to work with Fdtd and finite volume type methods. Okay, so just getting on now, just to give you a very brief non-technical overview of Fdtd. These are grid-based time-stepping methods. That Yi was kind of the person who brought them into the mainstream of electromagnetic simulation, but they go back much, much further, back to the 20s with Courant. in acoustics, what we're doing usually, or in the simplest case at least, is solving either the first order system for linear acoustics or equivalently the 3D wave equation. And a typical FDD scheme, the hallmark of it is that it's defined over a regular array of points. So spacing of given spacing and a given time step, and it operates as a recursion. So we loop through every value on our grid by making reference to previously computed values, and then we move on to the next time step. And the key parameter in these kind of methods is something called the Courant number, which is a dimensionless number. It can be thought of as the ratio of how far a disturbance can travel in one time step relative to the spacing on the grid. So we'll come back to that in a second. So when people work on test problems, people including us, usually start with the 3D wave equation over a box with perfectly reflective or Neumann conditions, mainly because there's a closed form solution in this case, so there's some sort of ground truth to compare against. So moving to a realistic setting requires, with issues that we've already seen a little bit today, so dealing with irregular geometries, frequency-dependent boundary conditions, as well as viscothermal effects over the interior, which are something we kind of want to highlight today because they're often neglected and quite important conceptually. And the numerical issues for Fdtd are, first of all, stability. So we want to make sure that if we have a complex simulation running, that the simulation behaves as we expect it to, that it doesn't explode on us. An issue that is also there, one of the big problems with Fdtd has to do with dispersion. So these are errors that accumulate in our simulations that can lead to more or less audible artifacts, depending on the algorithm we use. Okay, so today we're going to first talk a bit about Fdtd, we want to finite volume, and then say, sort of basing everything around the notion of energy-based stability analysis as our way of coping with some of these real-world issues. Okay, so let's first look at the way in which people deal with the stability problem in general for methods defined over regular grids. It's usually based on Fourier analysis of some kind. And strictly speaking, it applies really just to schemes that are defined over regular infinite grids. So what we're doing is we're decomposing the solution into wave components in all possible directions of propagation, and ensuring that wave propagation is bounded, the solutions don't grow exponentially while they travel. And for the wave equation, for schemes for it, what this always gives us is some upper bound on this Courant number that I mentioned. Okay, so suppose we now move to the simplest possible bounded domain, which is something I've illustrated here, something like a quarter plane or an octant in 3D. So there are extensions of this Fourier-based theory under some restrictions. So one is the one that I just mentioned, that we need to make sure that our region aligns with the grid. And also that the wall condition, whatever it is, has to be constant. So this, the extension of von Neumann analysis was developed by a group of researchers in I think, Sweden in the 70s, so Gustafsson, Price, and Sundrum. And really, you can think about it as an extension of Fourier analysis to the Laplace, spatial Laplace analysis. So suppose now we go back to look at irregular domains. So we've taken our region, which assuming it has some kind of continuous boundary, and we make a so-called staircase approximation to it. So every point that lies inside the domain, we consider the interior. Points that are outside, we consider the exterior. We draw a line around them all. The game then is to try to find stable terminations for this scheme, and that means trying to figure out what to do with all these points that are referred to by the scheme, which lie just outside the boundary, sometimes called ghost points. So, the natural idea is to try to apply these GKS-derived conditions to this more general case. So every time you see a corner here, you would simply use the conditions you would derive in the case of a quadrant, octant. And this, in fact, doesn't work. So I'll show you an example of this. So here is a rotated staircase region in 3D. And under certain rotations, this type of condition produces well-behaved results. Under other rotations, though, so the one on the right here, we see a slow but appreciable unstable growth. So at 25 degrees rotation, but not at 45 or 0. So there's kind of a problem with this kind of extension, and the reason is that this extension really it violates the assumptions that underlie GKS theory to begin with. Okay, so what we do in our group is we avoid frequency domain analysis entirely. We work only with energy-based analysis schemes. So here, we're looking for conserved or dissipated quantities in a numerical method as a whole, and then trying to bound the growth of the solution in terms of this function. So it's Lyapunov theory, basically applied to the case of simulation. So if we now think again about our system, say the wave equation, defined over some region, with, say, perfectly reflective boundary conditions on the walls, well, under source-free conditions, we have a conserved quantity for the Hamiltonian system. So written in terms of the velocities and pressures. And also, it's a non-negative function of the state, so it can be used to bound the growth of the solution as a whole. So when we're designing algorithms, what we try to do is to build in this property to our algorithms. So we have a numerical invariant. So if we're running through our time loop, updating, we have some quantity we can calculate that remains constant in non-negative function of the state. And using these kind of constructions, we have sort of another way to get to these Arup bounds that doesn't involve any kind of frequency domain analysis. But it's much more general than Fourier-based analysis because we can deal with irregular boundaries and also impedances that can vary all over the surface of the room. So we'll get to that. Brian will get to that in the second part of this talk. So these schemes, it's a way of designing schemes that's stable by construction. And it turns out as a bonus, you get a great debugging tool. So I'll just show you a little movie here. So here's a simulation in 3D. Here are two slices of it on the left. And on the right, we have the time evolution of the potential and kinetic energy components in blue and green, or in cyan and green. And then the total energy is a blue line up at the top. And if you look at it, the value is conserved to 16 places, which is about in the order of double precision floating point accuracy. So, and if you were to zoom in on that energy curve, you'd see the curve below, which shows you bitwise variation in the energy. So we use these tools in order to make sure there are no bugs. Because if we see any kind of variation beyond this degree, we know there's an error. It doesn't tell us where the error is, but we know there is one. Okay, so let's move on now just quickly to the case of frequency-independent wall loss. So the simplest non-trivial wall condition is a constant relationship between the normal component of the velocity and the pressure. And under source-free conditions, instead of having a conservation law, we now have a power balance. So we would expect our Hamiltonian, the energy for the system, to decrease over time, but monotonically. So it still allows us to get bounds on system growth. And this kind of thing is also very easily transferred to the numerical setting. So I think Brian will have a video later on that shows all this stuff. And then there's the extension to frequency-dependent wall loss. So I'm only going to talk about the locally reactive case today. It was interesting that one of the presenters brought up the non-locally reactive case. I think that's going to be the next thing that we try to incorporate. Which is best expressed in the frequency domain in terms of an admittance. So now we relate the normal component of the velocity of the surface to the pressure, but in the frequency domain you can express this as an admittance. But one constraint on this admittance is that it must be positive real, meaning that it's characterized by a passive relationship. And one representation, which turns out to be really well geared towards writing simulation, is a representation in terms of circuit network components. Because any passive admittance can be broken down into a set of circuit components that can then program directly from the map defining the circuit. And now we have an even more general balance because not only are we storing energy over the problem interior, we're also storing it at the boundary, so due to mass and stiffness. And now we have loss, and we have the same loss actually occurring over the boundary. And again, we can show that this total energy, which is now combining a sum of the energies over the interior and the boundary, is again monotonically decreasing. So we'll use that again to make sure our simulations are stable. So this is more general than any kind of GKS analysis, because we're now able to vary the conditions along the wall as you would in a real room acoustic setting. Okay, so just a quick aside about frequency dependent. Sometimes do this in Fdtd. One way that, is to take some non-trivial admittance function, look at the real part of it, and then run simulations over different bands, and then combine the results. And one difficulty here is that there is no such positive real function, which is real only, which is able to vary with frequency. It must have an imaginary part. So if you do this, you're neglecting the imaginary part of this admittance. So you're losing something from your simulation. So it's something to be taken account of. All right, so at this point, I want to pass it over to Brian to finish things off.
Okay. So I'm going to pick up by talking about staircase boundary conditions. So far we've seen that we can derive stable boundary conditions over kind of arbitrary regions, but they're still in a kind of staircase form. And the question is, are these any good in a room acoustic setting? So we can kind of get an idea of an answer by looking at a related problem. So just consider a sphere that we're trying to voxelize with a set of cubes. Okay, so you can show that actually, as the cell size decreases, the total volume of these cubes will actually converge to that of the sphere. But you can also show that the surface area of the union of all these cubes will not converge to the surface area of the sphere. So, if we think back to room acoustics, you know, a large part of the room decay times are from wall losses, and walls are boundary surfaces. So if we can't discretize a boundary surface properly, can we expect to get room decay times accurately simulated? So we can test this actually. There's a simple benchmark problem. Consider a rectangular box with rigid walls everywhere except at opposing faces, where you have frequency independent loss. And in this case, we can actually extract a family of modes with their modal frequencies and their decay times. So to test this, we can consider, you know, a staircase approximation to a box that's been rotated with respect to the grid in various ways, so that you can start to see staircase effects. And what we found was that, you know, indeed, modal frequencies actually converge in the limit of small cell sizes, or in the limit of high sample frequencies. But the T60 times do not for these modes. So, except for the one case where the box is aligned with the grid. So in the other cases, beyond, you know, any dispersion error, the T60s just don't converge. So we have to look back and think, well, okay, so Fdtd is good for, you know, it's a simple method. You end up with parallel implementation. Okay, so we've seen that frequency domain stability checking methods aren't reliable, and energy-based methods are a bit more reliable, are more reliable and allow us to derive staircase boundaries. But staircasing can lead to serious errors, and you know, this is kind of a problem that's beyond Fdtd. It's just a kind of geometrical thing. So we need a more general framework to, you know, apply these methods to room acoustics. So we've started looking at finite volume methods, which are very old, and they've been used in fluid dynamics, electromagnetics. The basic idea is you discretize an integral form of your equations rather than a differential form, and you average over cell volumes and over cell, you know, surface areas over the sides, and you end up with, you know, a simple difference equation where your parameters are in terms of cell volumes and side surface areas. And in the end, it's still just a simple explicit time integration. And when we specialize these to regular grids, you end up recovering, the well-known finite difference time domain methods. So if you use cubic cells, you end up with the basic Cartesian Fdtd. And if you use these rhombic dodecahedral cells, you end up with a finite difference method over a base-centered cubic grid, which is a bit more accurate in terms of numerical dispersion than the basic scheme. So it leads to a good approach to finite difference time domain. Use regular cells over the interior, and then specialize your cells over the boundaries to fit the boundary. And so here's just a few examples. So we have a staircase, grid, a fitted cell meshing where the cells were just kind of cut at the boundaries. This isn't actually the best approach for stability or for accuracy. So it helps to use a more adaptive grid at the boundary. And then we can extend this to 3D and even non-Cartesian grids. So here we have rhombic dodecahedral cells on the interior that are regular, and then at the boundary to fit it. Okay. So let's return to this benchmark problem. So we found that the staircased grids converge in the modal frequencies. Fitted grids converge a lot faster, where they just give you more accuracy for a lower sample rate. We found that the T60s didn't converge, but when you use fitted boundaries, indeed they do converge. So the problem really is the surface area approximation. So that's just a simple kind of benchmark problem. What about a domain that's less trivial, so not a box? So one thing we've looked at is kind of like fan-shaped theater geometry. And what we have here is 6 different simulations kind of overlaid in one plot using 2 different grids and 3 rotations of the domain with respect to each grid. So FCC and Cartesian. And what we find is if we use staircase grids, all the solutions kind of give us a different thing, or all the simulations give us a different answer. But if we use fitted grids, then regardless of the rotation of the domain, or the choice of grid, we get one kind of unique solution. And that kind of gives you a bit more confidence that you're actually solving the equation properly, because there should be one unique solution. So then, can we use energy methods for these approaches? Yes. Energy balances can be derived on unstructured finite volume meshes. So it helps to consider the most general case, even if we're using regular grids on the interior. And this is just to show an example simulation, that same theater domain, now with 6 different, there's 6 different walls and 3 different materials, and each one has up to 9 different resonances. So you can see the kind of energy calculation is still constant to numerical accuracy, and then you have various different energies that we calculate. So there's a stored energy on the boundary, for example, a lost energy that's kind of accumulated over time, and everything's stable to machine accuracy. Okay, another effect that we consider to be important since we're trying to do full audio simulations are viscothermal effects. So basically these lead to, over time or over space, decay in high frequencies. So here we're looking at the Stokes equation instead of the 3D wave equation. So it's just an extra term to the wave equation. And this extra parameter describes viscothermal losses. In general, it would depend on temperature, humidity, and frequency. We kind of consider it just as a function of temperature and humidity, which is kind of a first approximation. It's still quite a good one in room acoustics. And it leads to a more general energy balance. So now we have an energy lost through the interior, which is the energy dissipated due to viscothermal losses. And again, you can get a decreasing energy or strictly dissipated, and then you can get a discrete form, which is a stable scheme as well. Okay, so I'll just show now some examples of kind of what we can do with these methods. So, I talked about more general domains, but this is just a shoebox room for simplicity. 1,500 cubic meters, so medium size, and then a 48 kilohertz sample rate. So this is about 300 million points, or 5 gigabytes of memory in single precision. And so these are a few impulse responses we computed, just showing the effects of, frequency-dependent boundary conditions. So we can do, one resonance or two resonances at the same time, and then you can start to see the effect of viscosity in the high frequencies. So this is, one simulation with viscosity and without viscosity. You can see there's a really big effect. It's about 20 dBs, 20, 30 dBs in the high frequencies. So if you want to know, can you hear this effect? Of course you can. So I'll play some sounds here. This is with boundary conditions that are slightly more complicated, modeling a wall with porous layers, air gaps, and gypsum panels. So the coefficients were derived with the transfer matrix method and then fitted to this boundary condition we have. So I calculated some impulse responses and then I convolved them with this dry sound. So this is the dry sound. So this is with frequency-dependent boundary conditions, but without viscosity. So you can hear there's a shimmering in the high frequencies, so that actually shouldn't be there. When we add in viscosity, we get something that sounds a lot better. Okay, this is just another example, a dry guitar sample. And then with frequency-dependent boundary conditions, you can hear that shimmering effect again. Like, that's also a combination of numerical dispersion that's present. And then viscosity just kind of goes away. But I should say that, these sounds, you can't really hear the dispersion. If you just move the source or the listening position a bit further away, you start to hear dispersion effects. So this is an example of a sound with audible dispersion, I think. So if you can hear the attack is kind of wet. So that's actually dispersion. It's just kind of smearing the transients. So this is my last slide, well, second last slide. It's just talking about various approaches to trying to tackle numerical dispersion and finite difference methods. So we know that dispersion error is really significant in the basic scheme. There's better schemes out there, but still the ones we're using aren't ideal. Most of the schemes that we use are second order accurate, or second order in time, second order in space. As you probably know, if you raise the order of accuracy in either time or space, you can eliminate dispersion to some degree. So one standard approach is to use higher order spatial differences. So that leads to a scheme that's second order in time and fourth or sixth, eighth in space. And that's quite an old technique. You can actually show that it reaches the accuracy of pseudospectral method in the limit. But unless you use a kind of higher order time integration, the overall accuracy remains second order. So you'd have to use like a run-to-cut method. It's actually possible to get higher order accuracy in both space and time using only two-step methods, so methods that look back 2 steps in time. But it's much more delicate, and it requires stencils that look out in many directions, and then a kind of careful setting of coefficients that you have in the scheme, and then you can do it with either explicit or implicit time integration. So, both of these approaches lead to formal order of accuracy, which is, it means it's more accurate in your DC. So is that really important? Probably more relevant is a wideband accuracy, so accuracy in the dispersion over many wave numbers, or a wide range. So another strategy is to leave free parameters and kind of optimize the free parameters for numerical dispersion. And if we do this, we can get really isotropic error. So in this case, I'm showing you the dispersion error over a range of wave numbers. So at each kind of point on this axis, there's a range of directions. So you can see, since it's a fine line, that actually every direction is giving you the same error. And it's relatively small. So this is with high orders of isotropy. You can ignore high orders of isotropy and just do a kind of brute force optimization. And you can get really good results. So here we have less than 1% dispersion error up to the Nyquist. So that means basically you can use 2 points per wavelength. So, you know, we're using more points in the stencil, but it's the extra operations you require significantly are outweighed by the increased accuracy you get. And then we've actually started to test these large stencil methods on GPUs, and we found that the increases in compute times, increase sublinearly with the stencil size. So if you increase your stencil size, you don't actually lose that much in compute time, or require that much extra compute time. And this is mostly because they share a lot of points between notable updates, and you have very fast caches on the GPU. Okay, so now to conclude, so with finite difference time domain, there's still a lot of work to be done, and the main theme that we find is, you know, trading off stability versus accuracy. And finite volume generalizations have been useful in both of these regards. You have to be careful using some, you know, Fdtd methods that are in the literature because they're not actually so stable. But, you know, there are methods to derive stability as a whole. And then for these large stencil methods, you can approach boundary conditions with energy methods. But finite volume generalizations are a bit less obvious right now. So for now, there's a trade-off between accuracy on the interior and at the boundary. And then I said this already, the surface area problem is, it's a bit more general than Fdtd, so it kind of applies to every grid-based method. And then some future directions, some important problems that we're looking at. So finite volume on a large scale, there's a lot of issues. Meshing, how do you accelerate it on a GPU, CPU? Air absorption. So I mentioned that we're using a kind of first order approximation to a more general air absorption model. So in certain temperature and humidity ranges, these become important. And then one question, which I don't know if we'll get there anytime soon, is, you know, can we compare these methods to real world data? And how do you do that? Because you have to actually measure these input parameters, as we saw. So that's my part. So.
Okay. I think we're a bit tight for time, aren't we?
Yeah,
I'll try and keep it.
matters if we.
Yeah, I'll try and
We've
keep
got some stuff.
short. Okay, so first up, why would we want to use a GPU for computing a finite difference simulation? Finite difference time domain simulations have a natural data independence at each time step. You can update grid points in any order that you want, or indeed simultaneously. In fact, the entire state can be partitioned in any way you choose. And this gives us many options for computing the systems on parallel hardware. And this is ideal for GPUs, where typically you want to be able to issue a large number of threads to hide latencies in the system. Okay, so what I'm going to talk about here is what kind of performance benefit you can actually get by using GPUs compared to standard CPU calculation. Now, modern CPUs are complex parallel devices, just like GPUs are. So to make a fair comparison, you need to be maximizing the CPU usage just as you would optimize GPU code. If you don't optimize a CPU code, you end up with very poor benchmark performance. And we can demonstrate this in a very simple example. Okay, so let's take the very simplest 3D finite difference scheme for the wave equation. You've already seen this. This uses 7-point Stencil. We're going to simulate a small box room using 15 million grid points in each of the state arrays. And at 44.1 kilohertz, this gives us dimensions of 3.4 meters by 4 meters by 2.8 meters. So 38 cubic meters in total. And we'll run the simulation for 44,100 time steps, and we'll just use a simple fixed boundary for this test case. Okay, so the hardware that we'll test it on is an Intel Xeon E5 6-core processor, the CPU, and then an NVIDIA Tesla K20. As I want to demonstrate in this particular bit CPU benchmark performance, I'll first of all give the GPU times, best ones that I could get for this simulation on the GPU. Okay? And these were 1 minute 11 seconds at single precision and 2 minutes 26 at double precision. So they're the GPU times, yeah. Okay. So what we're looking at here are 3 different versions of the CPU code and the accompanying speed-ups that the GPU codes showed for each version. Again, these are split between single and double precision floating point. Now at the top we have the trivial single-threaded C code that was compiled using no other optimization. At single precision, this took 143 minutes, and the single precision GPU code compared to that is 121 times faster. Okay. And at double precision, the CPU code took about the same time, and here the GPU code is 59 times faster. Now, just turning on standard compiler optimization has a huge effect. So it's easy for the compiler to auto-vectorize and unroll the code in this simple case. Now, the CPU code now runs in 37 minutes single precision, 39 minutes at double, and the GPU speedups are times 31 and times 16. However, we're still only using a fraction of the CPU performance. Now, the final code uses POSIX threads, P threads, to parallelize the CPU code, as well as using compiler optimization as well. So now, the single precision code only takes 6 minutes to run, and at double precision is 7.5 minutes. At these speeds, the GPU is only 5 times faster at single, and just 3 times faster at double precision floating point. So we've come a long way from the original times 100 at the start. And you have to remember, this is only like a regular medium level CPU Xeon processor. If you had a newer 8-core device, you could get even closer to the GPU performance. Okay. So ultimately, the difference between the CPU and the GPU is down to memory bandwidth. The codes that we're running have a very low compute to memory access ratio, and so they're basically memory bandwidth limited. Optimization, either on CPUs or GPUs, is purely about maximizing the transfer of data from global memory through the cache and onto registers. Okay. Now in practice, this is actually quite difficult to do. Usually you can only achieve about maybe 50% of the potential memory bandwidth that's available. And in order to get more and more optimal performance, you generally end up with code that becomes more and more hardware dependent. Okay, so that's just a bit about CPU benchmarking and GPU performance comparisons. Let's see what we can actually do with a small cluster of 4 Tesla GPUs that is similar to what we've got there. So here we've got 4 Tesla cars connected together over the PCIe bus, 4 Tesla K20s. They're in one computer, one tower, with a very large power supply and a large fan as well. Because these things go off for heat. Each card has got 5 gig of global memory, so that's 20 gig in total. And each one can reach a theoretical maximum performance of 1 teraflop at double precision, or 3.5 teraflops at single precision. Now, of course, we're not going to get anywhere near to these kind of flop rates. Okay, so, as I said, these things are memory bandwidth limited. Okay, so for 3D Finite-Difference schemes, we can write CUDA code that uses all 4 cards simultaneously. Just use CUDA for that. We don't need to use MPI or anything. A single precision at 44.1 kilohertz. This translates to nearly 6,000 cubic meters for a 2-grid scheme, and nearly 4,000 cubic meters for a 3-grid scheme. 3-grid schemes are needed. You need to store 3 state grids if you're using viscosity in your simulation. And each of the state grids here is over 1 billion grid points, okay? So it's quite a large array, basically. And an example space would be 26 meters by 16 meters by 14 meters for a 2-grid scheme. Computation times that we're looking at are about 50 minutes per second of audio at 44.1 kilohertz. I have got some audio. Entirely sure how it's going to work. We'll see. Okay, so these are some audio examples using all 4 Tesla cards. It's a 3-grid viscosity scheme with a lossy but frequency independent boundary, so simple boundary. Now, when I do this, I actually don't run the simulations to get impulse responses. I actually input audio directly, and that way you have complete freedom to move the sources around, take as many outputs as you want, that kind of thing. So, let's see if this actually works. Yeah. Okay. So this is a dry, so we have dry inputs here and then the output simulation afterwards. So that was actually Steve playing guitar. Steve. And the output simulation, hopefully. Okay, that sounds a lot better actually.
I'm sorry, that cable's doesn't.
Yeah. Okay. Now another dry input for the guitar. And that's the output. Now with the vocals, this is like an opera singer in an anechoic chamber, is the original. And the outputs. And the final one here is it's actually a demonstration of moving the source during the runtime of the simulation. So what I put in is just like an alarm sound. And what I did was actually move it like actually really fast during the runtime of the simulation to get the dot.